Whether it be a family event, social event, or even a personal event, I'm sure at some point we all have consumed alcohol. This is the same for all of us, but what is not the same for all of us is how alcohol has affected our body. Alcohol metabolism is entirely dependent on the composition or genetic material composing the proteins and enzymes found in this metabolic pathway. Today we'll look at this idea of how genetic material points at the metabolic capabilities of the human body. This information can be used to understand the fragility and extraordinary power of our biological systems to put forth better decision making in our diet, exercise, alcohol consumption, and even drug consumption. I'm in my third year at the University of Nebraska-Lincoln with emphasis in biochemistry. My area of study has given me the opportunity to research, experiment, and observe the fundamental application of chemical reactions and systems within a biological setting. To observe why genetic material points at the metabolic capabilities in the human body, we first must look at the relationship between genetic material and metabolic pathways. And then next, we must look at how these metabolic pathways work. And finally, we must look at how these metabolic pathways determine the function of the human body. Let's now begin by looking at the relationship between genetic material and metabolic pathways. As we all know, DNA, or genetic material, is responsible for the uniqueness of all living organisms. The relationship between genetic material and metabolic pathways is relatively linear. DNA is transcribed into RNA, which is then translated into protein. Protein then acts as a chemical mechanism known as an enzyme, which can be used for chemical storage, digestion, or respiration. According to the 2016 scientific journal Molecular Aspects of Alcohol and Nutrients, pages 17 through 21, alcohol dehydrogenase, which is responsible for the digestion of ethanol in alcohol metabolism, is a good example of an enzyme found in the human body. Also, lactase, which is responsible for the digestion of lactose, is another good example of an enzyme found in the human body. Both alcohol dehydrogenase and lactase are good examples of enzymes derived from DNA that are the building blocks of what we'll continue to refer to as a metabolic pathway. Now that we've established a relationship between genetic material and a metabolic pathway, let's now discuss how metabolic pathways work. Metabolic pathways, just like the relationship between genetic material and metabolic pathways, is linear. Enzymes work together in a complex series of modification elements, beginning with the starting molecule. Molecule A specifically interacts with enzyme 1, and enzyme 1 induces modifications on molecule A by elimination, substitution, or addition of a chemical component to this molecule, rendering an entirely new product. This specific interaction can be exemplified in a relatively simple manner using a lock and key mechanism. Enzyme 1 in this example is the key, and molecule A is the lock. A segment of enzyme 1 interacts very specifically with a segment of molecule A. A modification occurs, a turn of a key, and then molecule B is then produced, which is an entirely new molecule. Referring back to alcohol, ethanol, which is the active ingredient in alcohol, molecule A in this instance, interacts with alcohol dehydrogenase, and a modification occurs resulting in the production of acetylhalide. Now that we have a basic understanding of the linear progression of enzyme 1, or molecule A interacting with enzyme 1 to produce molecule B, let's now not compare, but let's look at how these metabolic pathways determine the function of the human body. Metabolic function is the most fundamental process key to the survival and success of the human body. According to the 2003 scientific journal, The Phylogenetic Extent of Metabolic Enzymes and Pathways, the liver, kidney, brain, lungs, and heart are the most metabolically active sites in the human body. Using our knowledge of metabolic activity, we know it consists of molecules entering a pathway, modifications occurring, and molecules exiting the pathway. Using our knowledge of the human body, we know that molecules entering the pathway and exiting the pathway are vital to the functions that we all know as breathing, thinking, blood supply, and excreting unwanted molecules. Pathways that are disruptive leave cells deprived of necessary energy and nutrients, leading to illness, disease, and even death. As you can see, biological systems are a series of events dependent upon the event before. Beginning with genetic material, the building blocks are formed in the form of proteins known as enzymes. These enzymes then work together and coordinate themselves in a complex known as a metabolic pathway. These pathways then take molecules from start to finish in a complex series of modifications until the final product is formed. The product then can leave the metabolic pathway and perform its final duty as either energy, a catalyst, or even another enzyme throughout the body. Mishaps in genetic material lead to disrupted metabolic pathways, leading to complications and disease or even death. As you can see, as the chronological orders of events unfold, our everyday life is entirely dependent on the genetic material that we are composed of.